Ladies and gentlemen, welcome to my demonstration on Atena software, which will be broadcasted at the ACI Convention, Spring Convention at Orlando. So I'll be talking about our software Atena. We are exhibiting at the conference, so you are very welcome to come to see us at our booth number 304. And what we are presenting there is our technologies for advanced modeling and simulation of reinforced concrete structures. And our main product that we are presenting and that you can have a look at is our software Atena. So what is it about? What are we talking about? So our company is focusing, for those of you who have not heard about us, we are focusing on developing technologies for advanced modeling of concrete structures, reinforced concrete structures. And this slide provides a nice overview of our capabilities. So we can model bridges, containments, nowadays these offshore structures for electricity production are very popular. These offshore structures are, of course, steel structures mostly, but in this case, they usually have a concrete grouting. So our software Atena was used to design this grouting material in these offshore windmills. About our company, we are located in Prague, Czech Republic. So this is the famous picture of Prague Castle. We are a small company with about 20 engineers, most of them highly qualified, most of them with a PhD degree. And although small company, we are very internationally active. So we have representatives and offices, distributors all over the world, also in the United States. So this shows an overview where we are active all over the world. So we have about 700 companies or clients using our software and with about 2,000 users in 62 countries. This slide provides a very brief overview about our material model, which is the core of our software. That means the material model for concrete. So we are using this 3-parameter criterion, which you see on the left. And to simulate cracks, we are using this crack band approach, where we are using the softening law, which basically is used to control the proper energy dissipation during the cracking process. This is again the summary of the main laws of this material model. So in tension, we have this softening law when concrete starts cracking, where the area under this softening law represents the fracture energy. That means the energy dissipated during the development of the crack surfaces. In compression, we are using a plasticity-based model with this 3D failure criterion. And of course, we have to take into account the two aspects of the concrete behavior. That means first it behaves elastically, linearly elastically. Then we have a hardening, nonlinear behavior before the concrete reaches compressive strength. And once the concrete is fully crashed, we enter the softening regime, which is controlled by this linear softening law, which again is based on this energy approach to consider properly the energy dissipation also during the crushing process or failing of concrete failing in compression. Well, this slide just demonstrates that it works. And the best way how to show that the model is working is to participate in various blind prediction benchmarks that are organized from time to time by various professors usually, where before performing certain experimental programs, they announce some kind of a competition that they send out the description of the test and people try to predict. And here is a summary of some recent competitions where we usually obtain quite high, quite front places. So one of the first one was the Toronto competition in 1982. So you can see our history of modeling goes very far away. At that time, our software was not yet commercial. It was an academic model. And in this competition, this model received the first place. Then there are other interesting competitions. I would like to mention this one from 2014 by Professor Belletti, University of Parma, shear beams. And the reason I would like to emphasize it is that at that time, the winner was Dr. Il from Delft University using our software. So this kind of demonstrates that even if you are not sitting in our office and you are normal user, you can still obtain very good predictions. Another competition, 2015, very recent one, again from Toronto, where we received the first place for having a very good prediction. I will show more details about this competition because it was also published in this ACI journal 2015. So Professor Collins tested these very large beams with 19-meter span, 4-meter height. And actually, it was one beam, but it was, as you see, one side was not reinforced with stirrups, one side was with stirrups. So first it failed on the right and then on the left. So here you see some modeling, some results of our simulation. So this bottom shows the animation from the numerical simulation showing how the program predicts the crack propagation and development. And the peak load was obtained in the analysis was about 745 kilonewtons. In the experiment, it was about 685. But a very nice prediction of the crack pattern was obtained. Here is a comparison of the results. So this is from the right test, this bottom lower peak load. And this left graph shows the results from the left part of the beam with the shear reinforcement. So of course there the strength was much higher. As you can see, our predictions were always in this yellow zone, which was sort of the zone of fame with 10% error. And in both cases, we obtained good predictions, good crack patterns. So we were announced as winners in this competition. Here, of course, we have to admit that to have a prediction within 10% is quite lucky, because from our experience, we know that concrete is a very heterogeneous material, high scatter of material properties. So typically we know from other cases we can predict with the accuracy of, let's say, 15 to 20%. So in this case, it was quite lucky winning prediction. Now let me highlight some of the latest new features of Atena. So recently, last year, we have released the new version 5.9, and the main new features are the following, and I will be going through them on the subsequent slides. So one of them is that we have a new front end. This we call it Atena Center. So this front end helps you to navigate through the various tools, because the program has various options, various tools. We even have it in two products, one called Atena Science, Atena Engineering. So this is a very good way how we can navigate the user through the various options. And in addition, there is a very easy access to tutorials that you can just click here, open the list of tutorials. You can get a description of the tutorial, run the example, this gives you the possibility to explore how the data are prepared and how the model for such an analysis is prepared. So all this is now easily accessible through this Atena Center interface. Another new feature is the possibility to automatically generate reports in a Word file that you can then enhance and create a PDF file out of it. The other very new feature and very exciting feature is the possibility for durability modeling. So what do we mean by that? In the case of reinforced concrete, the main durability issues are related to the corrosion of reinforcement. So this new feature allows engineers to take this into account in nonlinear analysis. So if we somehow summarize briefly what is this corrosion process, what are the main stages? So first stage is so-called initiation, induction phase. This is the phase before the chlorides or carbonation, which are the main two phenomena affecting corrosion. Before they reach the reinforcement, which is usually a certain distance from the concrete surface. So this is the initiation phase. Once sufficient chloride concentration builds up at the reinforcement depth, the corrosion process starts. And as the corrosion is starting, we see an increased corrosion, and at some point, due to the expansion of the corrosive material around the reinforcement, we obtain a concrete cover, which creates cracks. That means the corrosion rate is increasing up to the point when the cover totally separates. There is a full spalling of the concrete cover, which again causes an increase of corrosion. And up to the point that we may have a structural collapse because the reinforcement is fully corroded. So these phases are considered in the model in the following way, that we combine a full 3D model with a one-dimensional model for the chloride or carbonation propagation. So how it looks like is schematically we can see on this slide. So we may have this kind of structure with some reinforcing bars inside. And then as an additional boundary condition, we can define some chloride, some environmental conditions on some surfaces. In this case, at these bottom surfaces, we define some chloride concentration. And then because the structure is somehow loaded, there may be some cracks that appear in the structure. And at the location of these cracks, of course, the chlorides will propagate faster, and we then see an increased corrosion of the reinforcement, which is indicated by these red zones here, indicating the amount of reinforcement corrosion, which in the software can be also described by either these 1D graphs or by some scalar quantities. So this is how it works. And now I would like to demonstrate application of this approach on one practical case, which was coming from United States. It was actually a project we participated on, and we made some analysis into the investigation of possible repair approaches for this Brooklyn Queens Expressway in New York. So this shows some segments of the model. So we modeled the concrete wall with the reinforcement. Then there were some stiffening cribs, the top slab with the reinforcement inside the slab. All this can be modeled in a very detailed way. And then there was this top layer. And the model also considers the removal of this top layer, which was exposed and cleaned and painted, basically repaired. And then a new layer was added, new layer of concrete. And then in this project, I will later on show you the effect of considering two materials. First material was high performance concrete. And now what this graph or what these figures are showing, I would concentrate your attention to this bottom right, which shows in time, depending on the year, how the corrosion of the reinforcement increases. And then at various times, we can subject this damaged structure to load. and we can estimate what is the load carrying capacity at various times. So this graph now shows this overloading approach at certain time. In this case, it is the very critical time when we have 180 years, so that means very old structure. And we can see there is actually very little load carrying capacity, cracking developing due to the reduced reinforcement. This bottom left figure shows the strains developing in the reinforcement. And what we typically obtained in this approach is that we obtain these low displacement curves at various times. So the yellow one is the original undamaged situation, which was in 1940. And that then at various times, we have a reduction of the strength. And we can plot it also in this graph when we show the strength of the structure, depending on the time as it is being decreased. And at some point there was this repair, which we have simulated by this high performance concrete, which of course increases the strength of the structure. And then due to corrosion, the strength is again decreasing until it cannot take the necessary loads anymore. So here is a comparison of the two materials, the HPC material and then the ultra high performance concrete. You can see for the ultra high performance, there was almost no reduction of strength due to concrete corrosion. So for this repair process, it was of course much better material. So now I would like to go another new feature, which is a new support in our Atena software for fiber reinforced concrete. As you know, fiber reinforced concrete is a material where after reaching tensile strength, there is typically a drop, but then the material exhibits significant ductility in tension. And this week have special models in Atena for that. There are various models, but in most of these models, any application consists of two steps. First, we need to determine this softening claw, which will be inserted into the program. One simple approach is to just assume this softening claw in a kind of simplified way as additional fracture energy necessary for the material. So this is one simplified model. But another more complex model is that program allows you to determine the exact shape of the softening claw based on experiment. Typically, it is a 4-point bending experiment or 3-point bending experiment, which are usually performed by the material manufacturers. And from such a test, we obtain this kind of curve indicated here by these two lines with black color. And Atena software allows you to perform fitting of this experimental result. And the result of this fitting is the shape of this softening curve that is then used in some practical case, like here. So first we perform fitting by fitting this 4-point bending experiment, and then this fitted curve for the softening for the material behavior is then used in some application case. In this case, we have these T-beams for this TBM method, where we have this boring machine which automatically is drilling the tunnel and at the same time placing these T-beams directly constructing the tunnel liner. So there are some new tutorials to support the engineers in this work. But in addition, there is this new tool we call APS FRC, which allows you to automatically fit your experiments from this 4-point bending test to determine the suitable softening claw. So here is a result of this fitting approach, where you start with some initial estimation of this fitted curve, and you see in only 3-4 iterations, you can obtain an optimized fit, which is indicated by this yellow curve. And then this is showing this application to some real projects in tunnel construction. All right, so this was about the fiber reinforced concrete support, which has been significantly improved. And another improvement or new feature is this cloud version of Atena. So this, if you go to this Atena cloud.cervenka.cz, you can create a virtual computer that you can then run, and you can run your Atena on a virtual computer, so you don't have to install it on your machine. Right now we are offering some free time for new users, but you can, of course, later on pay per use as you need it. So this is the interface of this Atena Cloud application, where you can use these various Atena products. We have added also new powerful computers, so you can, interesting thing about this application is that if you need to make some large model, you can you rent this computer, which has, for instance, 32 CPUs, 120 gigabytes of RAM. Another interesting application of this Atena Cloud or this cloud computer is that you can use it to run parametric studies. So if you, for instance, need to make a parametric study of some models, changing various parameters, for instance, compressive strength, tensile strength, or others, you can prepare these inputs, subject them to this Atena Cloud, and they will be distributed to various computers, and then you can obtain in a quite short amount of time the results from maybe quite extensive parametric study. Now I would like to also mention another feature which we have extended Atena recently and improved, that is the dynamic modeling. So let me show this presentation, which shows a simulation of a KMUS benchmark to demonstrate that the validation of this model on this example coming from France. So here you see the animation of this dynamic problem. Here I would like to emphasize that, as I showed you before, these benchmarks, those were really what I showed you before were blind predictions. What I'm showing now is not a blind prediction. It is this we did knowing the results, of course. And as you will see, once you know the results, you can obtain a very, very good fit. You see the movement of the structure. In the graph, you see the displacement of the fifth floor in this model. You can nicely see how the crack patterns were captured, and also this crashing zone at the bottom. And very good fit was obtained for this for the final low displacement diagram. And one more figure. Okay, now I would like to finish with the last new feature of our Atena model, of our Atena software, and that is the possibility to simulate 3D printing of concrete. So 3D printing of concrete involves two main, let's say, problems. One is that we need to gradually build a model. And most important problem is, of course, that we need to define laws for the material when it is very fresh. So Atena now supports that the user can provide these curves for the young material for the development of the various parameters. For instance, typically it is the Young's modulus, tensile strength, and compressive strength. And the next issue is, of course, to define the concrete path. And for that, we are using the trajectory, which can be either defined manually as a printing path, or the software now supports also the import of G-code. For those of you who don't know, but the G code is the computer language which directly controls the machine, the moving of the printing machine, and basically the whole operation of the printing machine. So this can be directly used as an input to define how the numerical model will be gradually activated. So let me show some video from one of our project, which we developed together with the Technical University of Dresden. In this project, the objective was the development of special machine which can print also sharp corners. So in this example, it might be slightly surprising that we are having sharp corners. Usually in 3D printing, the nice feature of 3D printing is that you can print some arbitrary curved shapes. But in this particular situation, the idea was to be able to print structures with very sharp corners. So this was kind of a demo house that was built, and it will and printed, and you can see one of the main applications why this simulation can help, because you can see this material is very fresh, and if you print too fast, the structure may collapse. So this simulation can help the designers or manufacturers of the printing of these 3D printed houses to properly design their printing speed or printing process to optimize it such that they don't have some excessive deformation or even collapses of their structures. So with this, I would like to again invite you to come to our booth 304 and visit my colleague Martin Berka. This is his picture, his photo. This is from the previous convention that we visited in Cincinnati 2019, I think it was. Then, as you know, due to COVID, most of the conventions were organized only in a online fashion. So we are very much looking forward to meeting you again. And I would again invite you to visit our booth. So thank you for your attention and see you in Orlando. Goodbye.
Atena program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name Atena. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.